that a cost function has. So I will start now a theorem, state a theorem. Telling the properties of the cost function. The cost function has two variables, y, the output level, and p, the price vector. So we will first see the properties as a function of y, and then the properties when p is fixed, and then the properties as a function of p when y is fixed. Okay? So first, let us fix p, prices. Then C is non-decreasing. And lower semi-continuous. Well, I will give full mathematical proofs, all of them very easy, of all these results. But first, some comments from the economics point of view. You don't need to be a candidate to the Nobel Prize in economics to understand that the cost function is non-decreasing. If you want to have a higher output, then you need to spend more money. I mean, this is okay. Then, but what about lower semi-continuity? Does it has any economic meaning? Not at all. Zero meaning, because it cannot be empirically tested. With a finite number of observations, which is that you can do, it's impossible to know if a function is continuous or lower semi-continuous or upper semi-continuous or whatever. But this is a technical property that follows from our definition. Then another thing for which no Nobel Prize is required is that to produce zero, you need to spend zero money, because there are no fixed costs here. Okay? Then, slightly less obvious, is that as the output level goes to plus infinity, then the cost goes to plus infinity too. These are the properties as a function of y. Now let us fix y, and let us see the properties as a function of p. So C is non-decreasing, non-decreasing. This means if P increases component-wise, I mean, for the new P, all components are greater than or equal to the components of the initial P. So all the prices increase or remain the same. Then clearly you have to spend more money. Again, an obvious property for economists. And superlinear. You know the meaning of superlinear? Or you know the meaning of sublinear?
Yes, the p of x plus 1 is less than x plus 1.
Sorry?
Some function argument is x plus y, then less than equal to fx plus fy.
Yes, I mean, well...
Function is homogeneous plus, yes.
I mean, sublinear means the function is convex and positively homogeneous of degree 1. Superlinear, you change signs. So means the function is concave and positively homogeneous of degree 1. Okay, or equivalently, it is positively homogeneous and super additive. Okay, this one can prove it's equivalent. Mathematically, it's quite obvious. I could prove it without writing a single line, but I will write 1 or 2 lines. Okay, and another property that if you don't pay enough attention, you will say you are writing a tautology, is that either this is finite or plus infinity. This should actually be a tautology, but it's not when I say even this is real for every p, or this is plus infinity for every p. Okay, it cannot be for some p's finite and for some other p's plus infinity. For all of them, the same. If instead of writing twice for every p, I write it only once at the end, then I'm saying nothing. I'm saying that a number is 0 or plus infinity. In this case, well, these are the properties of a cost function. Why do I say these are the properties? Or not, they are properties that a cost function has to satisfy. Because we will prove that these properties are also sufficient for a function to be a cost function. So we will see, but not today, not tomorrow. Why not? Because I use techniques of advertising. No, when you are watching a soap opera on the TV, they just cut at the most important part, so you are eager to connect tomorrow again. Then, okay, so the interesting thing is that, which I will prove, and this is the duality. Wait a second. Is that whenever you have a function with these properties, you can find a function f which interpreted as a production function induces this as the corresponding cost function. Please. The only assumption on f is that it's upper semi-continuous. So these properties are satisfied for the cost function associated with an arbitrary upper semi-continuous function. Okay? Yes, I mean the cost is finite, no matter the price, or plus infinity, no matter the prices. That's the meaning. And these are quite, all these properties are quite easy to prove using mathematics, not just economic intuition. But it will be more interesting to see this converse, that whenever you have a function satisfying all these properties, then it can be interpreted as a cost function, because there is some production function which we will construct explicitly, and this function is not unique, but we will construct one which has all the nice properties that one has the right to ask for a production function. Okay? Then, so let's recall the definition of the cost function. This is the minimum of Px subject to f of x greater than or equal to y. Non-decreasing. I mean, we fix P and we study the behavior with respect to y. If y increases, this feasible set becomes smaller, then we are minimizing over a smaller set, then the infimum increases or remains the same. So this is the non-decreasingness stated here. Okay? Then, lower semi-continuity. I think I didn't define lower semi-continuity, but I defined upper semi-continuity. So a function, let's say f, is lower semi-continuous if the lower level sets are closed. And again, you could prove, similarly as what we did in the case of upper semi-continuity, that this is equivalent to saying that the epigraph. Okay, now we are considering lower level sets. So if this is the level, this is the set. And the epigraph is what is above the function. Okay, again, it's equivalent. It's a matter of changing signs. There is nothing new here. I mean, a function is lower semi-continuous when it's negative, minus f is upper semi-continuous, if and only if. Well, okay. And this amounts to saying that the lower level sets are closed. Then consider any lower level set of this function. P is fixed. So it's as a function of y, level alpha, I fix a level. Okay? And I consider a sequence, yk, here, converging to some y, and then I have to prove that this y is also in this lower level set. Do you agree? Well, then, that yk belongs to this set means that C of yk p is less than or equal to alpha for every k. Okay? By the way, less than or equal to alpha, this means that it's not plus infinity. So the minimum is a real minimum with attainment. Okay? And then this means that this minimum for yk is attained at some x. So you have this equal to p xk for some xk satisfying f of xk greater than or equal to alpha. Okay? So, Where does this sequence live? This sequence xk lives in this half space px less than or equal to alpha. So all the components, repeating an argument I already used, we are on a compact set. Okay, because let's say pi xka is less than or equal to the sum, because every term in this sum is non-negative. So each term is less than or equal to the sum, and this is less than or equal to alpha. So xka is between alpha divided by pa, which doesn't depend on k, and 0. So all the variables in this sequence, all the components in this sequence are bounded by bounds that do not depend on the particular element in the sequence. Okay? Then this sequence has a convergent subsequence by compactness, which without loss of generality, we can assume it's the sequence itself. So we assume that xk converges to some x. And then from this inequality, which I repeat here, pxk less than or equal to alpha, taking limits, we get that px is less than or equal to alpha. But on the other hand, xk is in the upper level set of f corresponding to level y. This is set here. And xk converges to x. And this upper level set is closed by assumption. Then the limit also belongs here, which means that f of x is greater than or equal to y. Meaning what? Meaning that you can produce y with this input vector. Now, what can you say about C of yp? Because of this definition of C of yp and the fact that x satisfies this inequality, x is a feasible element here, so the minimum is less than or equal to the value corresponding to some feasible value, in particular to px. And px is less than or equal to alpha. That's the end. This means that y belongs to the lower level set of C level alpha, thus proving that this lower level set is closed. That is to say that the cost function is lower semi-continuous as a function of y. Okay, so it's a little bit more technical, but anyway, it's easy. C of 0p is equal to 0 if y is 0, x equals 0 satisfies the constraint. F of 0 is greater than or equal to 0 because f only takes non-negative values. So we get here p times 0, which is 0. And it cannot be smaller than 0 because this is non-negative. So this is the proof of this second property. Third property. Third property. We fix a positive number, and we have to prove that for y large enough, C of yp is greater than k. Then I consider the following number, which I am going to call u sub k, because it depends on k, which is the maximum of f of x subject to p of x less than or equal to k. Do I have the right to consider this number? Am I committing some abuse of notation or something? I mean, I can write supremum, this is no problem. Supremum could go to plus infinity, but I'm writing maximum, which excludes that possibility, and I am so saying that it is attained. Why? Because, again, this constraint, together with the non-negativity of the strict positivity of the prices, Pi, and the non-negativity of the components of x, means that we are in a compact set. Okay? And then, can we apply Weierstrass theorem? Sorry?
Capital F is not given to continuous.
Sorry, I didn't.
Capital F is not given to a continuous.
I mean, f is not assumed to be continuous. That's your point. Very good. That's the point. But in spite of this, we have the right, because, I mean, the Weierstrass theorem that you may be, those of you who are teachers, who are explaining to your first year students, if a function is continuous, on a compact set, it has a maximum and a minimum. But this is a consequence of a theorem that Weierstrass maybe didn't state. If your function is just lower semi-continuous, it attains a minimum. If it is upper semi-continuous, it attains a maximum. If it is continuous, it is both. Then it attains a minimum and a maximum. And here it is upper semi-continuous. If you look at the usual proof of Weierstrass theorem, you will realize that to prove the existence of a maximum, you are just using upper semi-continuity, or for a minimum, lower semi-continuity. By the way, a comment also to those of you who are teaching maybe first year mathematics. Then you are teaching wrong, as I have been teaching wrong for many years. Because when we teach the Weierstrass theorem, we used to say, look, this condition of compactness and continuity are sufficient for the existence of a maximum and a minimum, but obviously they are not necessary. And then you give easy examples. This is a lie. This is a lie. Why? Observe at the statement of Weierstrass stream value theorem. Assumptions: continuous, compact. Conclusion: there is a global maximum. Do you see any topology in the conclusion? No. So the topology is a tool. Conclusion: you are free to choose the topology. Of course, where all the examples you give are in Rn, so you are implicitly assuming that it has the Euclidean topology, but you can choose the topology. I published a result saying that this version of Weierstrass, lower semi-continuous minimum, is if and only if. This means if you have a function and a set such that the function over the set attains a minimum, then you can endow a topology on the set for which the set is compact, and the function is lower semi-continuous. So is if and only if you are allowed to choose the topology. But of course, for your first year students, you were not telling lies, in fact. Okay, yes. Sorry, I cannot hear you.
The last line that you said about the other way around, if we can choose the function to be lower semi-continuous, then we can reduce the topology.
Yeah. Should I repeat? You mean?
Yes, yes.
Yeah, I mean, suppose you have a function defined on a set. There is no structure on the set. Okay? But you know that the function attains a minimum on that set. Then you can find, it's very easy in fact, you can find a topology on that set that makes this set compact, and under the same topology, the function is lower semi-continuous. So you can state in a if and only if way. Okay, and then when I obtained this result, which was very difficult for me to publish, I was very excited to get that result, but no, some people liked it, and they say, you should submit it to this journal, that journal. I got infinitely many rejections until I got it published. I mean, I'm not ashamed of having rejections. I would be ashamed of not getting rejections, because this means I never submit a paper. Okay? Professor Mishra said that he never published a paper when I said maybe because he didn't submit. But you know, I was the editor-in-chief of optimization between 2006 and 2013. And then I recommended my successor, it's a lady, Professor Christiane Tamer. We are very good friends and co-authors. And when I visit her, I stay at her home with her family. She stays at my home with my family. Very good friends. And one of the first things she did when she took office was to reject one of my papers. But okay, this means this was very honest, no? Well, but then when I produced this paper, so hard to publish, but now it's published in optimization letters. Then I think, okay, and what about the classical version, the first year student version of Weierstrass theorem with continuous and both minimum and maximum? Is it the same? I produced a counterexample. Okay, so I forgot, I don't remember now, but I produced a set and a function for which there is a global minimum and a global maximum on that set, and there is no topology that makes the set compact and the function continuous. But if you add to the condition the fact, I mean, the trick that we have been using here, adding an extra constraint that does not change the optimal value, the same as one does to prove that the existence in a Euclidean space of the closest point on a closed set. One catch with a ball. But adding this extra condition, then it becomes again if and only if. Again, if you are interested, I can send you an electronic copy of that paper. Okay, but here, everything came from the fact that here there is the maximum does exist. And then what happens if I consider y strictly larger than this UK? So I want to produce y. So consider x that makes this possible. And remember that y is greater than UK. Strictly greater, then since f of x is strictly greater than this UK, which is this maximum, this means that this x is not among these. If this x satisfies this constraint, then f of x is smaller than the maximum, which is UK, and this is not the case. This means that this x satisfies the opposite inequality. What have we proved? That every feasible x satisfies this. So the smallest cost to produce this particular y under this p is greater than or equal to k. K, sorry, this should be capital K. This is the dependence on k. Okay? So this is k, capital K. This is capital K. There is no little k here. We are not considering sequences. So then this is the conclusion. I mean, every value k, no matter how large is it, is overcome for sufficiently large y. If you take y greater than this number, which depends on k, then the cost will be higher than uk. So this means that we have this property. Okay, so now the properties with respect to y are already explored. Now it's the turn of properties with respect to p, fixing y. Let me write the definition once more.
It's not required to prove that UK is unbounded.
UK is?
The UK.
Is a finite number.
UK is a finite number for any given k.
Yes.
But for UK has to be proven to also increase. Otherwise, that
I don't care about the properties of UK.
we need also y tends to infinity.
But what is the meaning of this? That I can take values of this as large as I want, but setting y as large as needed.
Yes, yes.
So I want this to be greater than k. And I can achieve this by setting y larger than this number that depends on k. Yeah. No, the dependence on k, it's clear. I mean, if k increases, this becomes larger, the maximum increases. So UK depends increasingly on k, but this is not needed here. Yeah. Pardon?
You consider the product of P and S, X is less or equal to K, but in last time you consider PX.
No, I'm not sure I understand your question, but I mean, you agree with this inequality? So you are asking about this?
No, there it is written Px less than equal to
Exactly. Exactly. So I am saying this f of x is greater than uk. This means this x does not satisfy this inequality, because otherwise f of x for this x should be smaller than the maximum, which is uk, and it's not smaller, it's larger. So this means that this x does not satisfy this inequality. So it satisfies the opposite inequality. And then because we are considering, I mean, this expression is every x satisfying this inequality. For such an x, this is greater than k, then the minimum is greater than or equal to k. Actually greater, because the minimum is attained. So if you want to refine the proof, you can write here greater, but it's true, but it's not necessary. Okay? Well, now, let us fix y, and let us examine the dependence on p. If p increases, component-wise, Because x is non-negative, then this increases or remains the same. So the minimum increases or remains the same. So this is the non-decreasingness property. Okay? Is this clear? Superlinear. I said for some of you, the proof is without writing a single line. Because imagine here instead of minimum it says supremum. Then we are dealing as a function of P. This is the support function of this set. And support functions are sublinear. This should be with supremum. With infimum we change signs, then it is superlinear. But since you may not like this argument or may not be familiar with support functions, etc., let me give a direct proof. I said superlinear means two properties. One, positive homogeneity of degree 1 and concavity. Positive homogeneity of degree 1 is obvious. If you multiply P with lambda strictly positive, P occurs here, this lambda positive comes here and comes out. Finished. The positive homogeneity. Now about concavity. Okay, so for concavity I have to consider two price vectors and a lambda between 0 and 1. And I have to examine C of y 1 minus lambda P1 plus lambda P2. Okay? I should end up proving that this is greater than or equal to 1 minus lambda C of y P1 plus lambda C of y P2. This is what I have to prove. This is concavity. Do you agree? Now, look at this expression, at this definition. I mean, it's this definition, but with P replaced with this convex combination, okay? But let's consider a feasible X. X such that f of x is greater than or equal to y. And then what is the cost associated to this particular x under this price vector? This is 1 minus lambda P1x plus lambda P2x. But look, I mean 1 minus lambda and lambda are non-negative. So we can replace here P1x with C of y P1, because P1 of x is a feasible cost under P1. So it's greater than the smallest cost, which is C of y P1. Same here. Nothing else. This is concavity. I mean, we are here reproducing the classical proof that the support function is convex, sublinear. Then, about the last property. If C of yp is real for just one p, this means that there is some feasible x satisfying this constraint, but this feasibility does not depend on p. It simply depends on f. So if this is finite for one p, is finite for every p. And this is the proof. Okay? If it is infinite for some p, it is plus infinity for every p. Because if it were finite for some p, then it would be finite for every p. So as you see, very simple properties. None of them is difficult to prove. Almost all of them have a clear economic meaning. The surprising thing to me is that these properties are characteristic of cost functions. As I already said maybe twice, if you give me a function satisfying all these properties, I will produce a production function which induces your function, the one you have given to me, as its associated cost function. But we will see it not today, but maybe tomorrow, I don't know exactly. Okay. Then, it may be good to see some example. Oh, yeah. Okay, thank you.
So the function which satisfies all these properties will be referred as a cost function.
Yes. Yes, yes. Probably the most popular, or one of the most popular production functions in economics is the so-called Cobb-Douglas function. Have you heard about it? Two different people, not a composed name. And they introduced this function in 1928. If I'm not wrong. No, because this is recent, no, I suppose. No, and also they are economists. They were economists. I don't think, but who knows? So is the following, a function with the following structure. A times product A and the alpha i's are constant, positive constants. Okay. Why are these production functions so important in economics? First, because they are simple and you can easily handle them mathematically. And second, because they are empirically relevant. So in many real-world situations, the production function follows more or less this model. One typical example is a model in which there are two inputs, capital and labor. capital, and labor. And it was observed, I don't know how long ago, maybe in 28, when they introduced this function, that they have such a, the production function has approximately this expression with, if I remember well, with alpha equals 0.25 and beta equal 0.75. Empirical observation. Okay, labor is, if I remember well, labor is more important than capital. Well, they are used also as utility functions in consumer theory. A utility function can be regarded as a production function. It's a function that produces us utility, happiness, or whatever. Well, so let us compute the cost function associated to this function. It's an exercise in calculus. The only thing you need to know is KKT theorem. We have time. I'm not sure how long it will take. I'm not sure because I'm not confident in how many mistakes I will make when making computations. But if you watch me, I can try to avoid. Okay, let's count how many mistakes I make, okay? So, we have to minimize the sum of pi xi subject to the production function being greater than or equal to y. The optimal value is the cost function. A is a constant. A is a constant and the alpha i's are constant too. A does not play any main role. Okay, then we can use KKT theorem. Here, to put things simpler, the linear independence constraint qualification is whole because the gradient of the constraint function never vanishes. So we are free to use KKT theorem. I don't know if everybody is familiar with KKT, but you are going to probably to tell us about convexity and so on. Then, so let me compute the Lagrangian. Just one multiplier. Okay, this is the Lagrangian. And the KKT conditions are gradient with respect to x equals 0, so partial derivatives. So I take partial derivative with respect to xj. So here xj to alpha j would become xj alpha j, xj to the power alpha j minus 1, which means we are dividing by xj. This is equal to 0. And lambda non-negative, and the complementarity condition Okay? Now, I claim that lambda must be strictly positive. Do you agree? Look at here. If lambda were 0, then Pj would be 0, which is not the case. Our prices are strictly positive. So lambda is positive. Therefore, this is equal to 0. Okay. No, I don't want to make mistakes. Yes. So from this equation, we can do two things. One is to replace this with y. This is what we have observed here. And after that, we can solve this equation for xj. Okay? Where is the... yes. Now, you should finish because you know it much better than me.
No, I recognize.
Yeah, I know that you are very familiar. So now I feel ashamed to do it in front of you. So you came in the wrong moment. I'm trying to compute the cost function associated with a Cobb-Douglas function. Okay, then this is xj. And we have to come to this expression and replace xi with what we have obtained here. Okay? So we get y equal a, so lambda will be raised to the power sum of alpha i's, because it will appear in every factor. I'm defining alpha as the sum of the alpha i's. Okay? Then what else? The same with y. And then the product of alpha j over pj power, well, but it's I. So alpha I over pi to the power alpha I. Is this correct? Then moving y alpha to the right hand side, I get 1 y1 minus alpha okay. I think something is missing or not? Not yet. There was alpha j here. Where did alpha j go? Alpha j divided by pj. Did I forget the alpha j? No. Seems correct. So now I solve for lambda. Lambda would be y over 1 over alpha minus 1 times alpha a to the power 1 over alpha minus, okay, and then the product, since I'm moving to the other side, I change the order, and this is alpha I divided by alpha. Is this correct? So now that I know alpha, lambda, I know xj.
It's not regular. We require function of pi.
Yes.
Pi xi. So
Yes, but
it will be alpha lambda.
yeah, you are right. I can skip this step. So sum of pi xi. I mean, what you are suggesting, if I understood correctly, is to move this to, and then I get sum and alpha, lambda y alpha. Sum of alpha I, which is alpha. And then, given this lambda, then we get, multiplying with y, this minus 1 disappears. Then I associate these two factors, and I get y over a, 1 over alpha, and then the product. Well, it's a simple computation, but the result is interesting. Do you observe anything interesting in the result? I mean, this is the cost function, okay, important. This is C of yp, because this is the optimal solution for the optimization problem. So the interesting fact, sorry? No, CIP, PIXI. Is there any mistake or?
Saying that this is independent of the term xi. Is this the observation?
No. Of course, the result should depend only on y and p. Xi is the optimal solution. No. The interesting observation is that the cost function is also of the Cobb-Douglas type. Is also of the same type as the production function, Cobb-Douglas, because, I mean, forget all the constants. Y is a constant because we are considering as a function of p. This is a constant. Everything is a constant. Alpha is a constant. and then you have the product of the variables raised to a power, a constant power, times a constant, which is a new a. Okay? So this is interesting, and I think we are going to use it sometime in the future. Okay? So now probably it's time to finish. No, you have no questions or comments?
If you have any questions, you can ask. Any doubt?
Yes. I mean, I think everything was rather elementary, understandable, I hope, but then I wouldn't like you to get lost. There is no need because everything is simple. I mean, it's not something very sophisticated. Yes, I mean, Cobb-Douglas is used for several reasons. One is that it's very simple, and second, because in many real-world problems are realistic.
Like what kind of real problem? Like as a mathematician, if I wanted to like see economics, or if I wanted to use all of this, where do I use it?
I mean, no, as an economist, I mean, you should do econometrics. We should study an industry and see what happens with the inputs, the outputs, etc. Study their technology, what are the costs associated, etc. And then and see if a Cobb-Douglas function fits your model. I mean, if your technology, the technology of the firm or the industry you are studying, is appropriately described by a Cobb-Douglas function. You have then, I mean, but it comes from observations. Okay, you have to observe data from that industry and then try to fit
That
the
is
constant.
function
To
in that
try
form.
to see exactly if there is a constant a and constants alpha I, such that the corresponding expression fits more or less the situation you are studying. Mhm. But this is done by econometricians. No, we mathematicians do these things. They are
So
simple.
exactly I asked.
ये प्रोडक्शन फंक्शन है, प्रोडक्शन इंडस्ट्री में हर जगह यूज मिलेगा इसका.
Production function?
It is a production function.
Yes, yes.
So in economics, wherever the production is involved, it is involved.
Yeah, no, but her question is why this model, Cobb-Douglas? In production function, this is the basic concept. But why Cobb-Douglas functions are so popular? This was her question. Any other questions or comments? No?
So although we started from macroeconomics, microeconomics, the title of the course is on economics, but we feel like we are attending mathematics.
No. The title of the course is Convexity and Duality.
Yeah.
Economics comes in the end.
Yeah. My request
It's a long title, and economics is postponed to the last possible moment.
No, I'm just curious to know, is there any book can you suggest that, although it will have economics flavor, but obviously things on mathematics?
Well, I mean, I suggested this book.
This book. Okay.
Yeah,
This book is,
there are electronic copies of this book.
okay.
Which
it seems
one?
This book is on concavity.
On?
Concavity.
Concavity, like it seems.
Generalized
Concavity.
Yeah, but it's you change signs. Because, I mean, this book is written basically by economists. And economists, unlike mathematicians, they are optimistic people. And they like to maximize. And we are pessimistic, we like to minimize. And then because they maximize, they consider concave functions. And we consider convex functions.
That's why concavity is there.
Yeah, because it's,
We are consumers, so we want to minimize the cost.
yes,
And they are
exactly.
producers, so they want to maximize
Yeah,
profit.
that's the reason, exactly.
So
Exactly.
we are somewhere in
But-
the equilibrium in this.
But there are also good books that are used in economic courses on microeconomics. Probably, I'm not very familiar with the literature, but a very good book, which is already 30 years old, I think, is the book. One of the authors is from my city, Barcelona. Is an emeritus professor of another university, UPF, Universitat Pompeu Fabra, Andreu Mas-Colell. He spent most of his academic life in the US, in the best universities there, and at some point in time, he was considered to be a reasonable candidate to the economic prize in economics. He has also very deep books from a mathematical point of view. He has a book called, I'm not sure about the title, but Equilibrium Analysis, a Differentiable Approach, in which there is a lot of differential topology. Not a trivial topic at all. Okay, so there are three authors of this book. One is Mas-Colell, Winston, and Green. I don't know the other two authors, but Mas-Colell, of course, I know. Yeah.
May I take a simple book for these things?
Pardon me?
May I say a simple book on these
Oh,
things?
please.
Generalized Convexity and Optimization, Alberto Camini and Laura Martin.
I'm sure it must be a good book,
It is
but
good.
I'm not familiar with it, so I cannot.
It is the lecture note series of Springer.
Yeah. I know the authors, and yes.
But
Alberto,
it is very simple, and all kind of properties of these functions are given. They're like they are convex or quasi-convex or whatever.
Yeah. I knew the existence of that book, but I have never looked at it. But it must be a good book. I know I know better the son, Ricardo, than the father. But, okay. So, any other questions or comments?
And on the rightmost side, if you look, then we are getting the similar result to which mentioned by Prof. Douglas. So here A is constant; it has a fixed value. So outside the product function, we are writing here y upon A. So y is also has a fixed value. Y has a fixed value.
No. Yeah, we are fixing y. I say the cost function is of the Cobb-Douglas type as a function of p, with y fixed.
Y is revenue, right?
Yes. No. The output. Yeah. Yes. So as a function of the prices.
धीरे धीरे पढ़िए समझ में आ जाएगा.
So there is no question. We can conclude the session now, and
Okay.
from tomorrow we will have the lectures from 10 a.m. in the morning. I think I shared the schedule with the WhatsApp. Okay. And it will be good if you try to summarize the lectures of every day, lecture 1 and lecture 2. You try to write down the summary, and maybe we will share a Google form where you can